Hey folks, my name is Ethan and I'm the founder of Nux.ai. Nux stands for New User Experience, where our goal is to help you build AI applications. And today we're going to walk through one of the critical building blocks of building AI applications, which is the concept of vector embeddings. And we'll walk through a diagram. We'll kind of build up the knowledge as we go. And then we'll walk through some actual code that both uses embeddings and manipulates them. So let's dive into kind of the very beginning, which is really how computers understand the real world. And if you remember from really any kind of computer concept, course, class, explainer, etc., computers understand everything in binary. Right? Ones and zeros, right? Everything gets converted into ones and zeros, and that's because of like logic gates and transistors, etc. But we don't have to get into that now. But at its core, everything that we understand, that computers understand, is ones and zeros, right? And so let's say an apple here can represent 1, 0, 0, 1, right? It's a pretty simple object, but what happens if we have a more sophisticated object, let's say like an MRI, right? How do you represent an MRI in binary? Well, you don't. You need what's called a vector representation. So said differently, we need a model to convert an MRI into the corresponding unit of measurement that a computer understands, right? And that's what an embedding is. So let's get into what an embedding is mapped into. But first, let's think about our high school geography, where we have an XY axis. And let's say we have the term king here, and king from, again, assuming we are able to convert this string into a numerical representation, king is plotted on this plane as 1, 0, right? And let's say queen over here is 1, 0. So we have 0, 1 and 1, 0, sorry. And now we have the vector representation of both king and queen, and so now the distance between them is how similar they are, right? So king and queen are pretty simple examples, but what happens if we want to now map an MRI on these planes? Well, x and y doesn't contain enough dimensional depth that we need to calculate the distance between an MRI. So said differently, there are only so many combinations of x and y that we can have for this really densely packed information, an MRI. So now what we need to do is convert this MRI into a multi-dimensional array, right? And a multi-dimensional array is basically a bunch of floats, right? And a float is you have a whole number or 0 and a bunch of leading decimals after that. So a high significant figure. So 1.0001, 1.0002, etc., etc. And so now we can map this concept of an MRI onto a plane that has this number of dimensions. So ChatGPT has, out of its box, I think the GPT-4 is 1024 dimensions. So imagine we have X, Y, Z, A, B, C number of axes, right? In a multi-dimensional plane where the number of axes is this number of dimensions. So it's really challenging for our brain to kind of conceptualize this, but at its core, this is how AI applications convert text, image, video, audio into a representation for us to do sentence completion like ChatGPT, product recommendation like on Shopify, image recognition like on Google Images, etc. It's all converted into these vector representations. Okay, so hopefully that makes sense as like a core foundational explanation of what a vector embedding is. Let's dive into some code, and hopefully this isn't too overwhelming. Let me just clear all of these outputs so we start from scratch. Right, so word2vec is a very like foundational embedding algorithm that is just converting a bunch of strings into, again, their vector representation. So we've got these sentences, and we're saving these sentences as a training data set into this word2vec model. And then we're going to then send this term example into that same model. And then it's going to print out what that example vector representation is. So here we have, like I said before, we have a bunch of floats, right? So this is a float in an array of arbitrary dimension, and we could just print how many dimensions we have in this example. So it's a 100-dimension vector representation for the word example, and we're actually specifying that right here. Cool. So word2vec is a very foundational algorithm that converts strings like I guess the term MRI into a vector, right? And so let's do a little bit more of a complicated, more interesting approach for converting these vectors into embeddings, and that's to use BERT. And BERT was one of the outputs of this transformative paper called Attention is All You Need. And Attention is All You Need introduced the concept of transformers. And transformers are the building blocks of these these vector generative models. And we're using these models to encode, again, strings, video, image, audio into these vectors. So let's dive into this. I'm just going to import this library, and then I'm going to take the first paragraph of the Wikipedia page on Japan, and I'm going to split it by period. And so what that tells me is each of these sentences in the paragraph is its own independent thought, right? It's because we want to split it by what we deem an independent idea, so that when we do retrieval, we're retrieving each of these independent, in this case, sentences for response into our workflow, right? And so first, what we're doing is we're splitting this corpus, this paragraph from Japan, into those sentences, right? And then what we do is then we encode each of these sentences into an array of floats. And here they are 384 dimensions. And one important thing to note is that the number of dimensions that you have in your vector representation doesn't always correlate to the speed, the accuracy, the informational depth, etc. There's a lot of trade-offs, which we'll get into in a different video. So we're converting each of these sentences of the Japan paragraph into their vector representation. And so then what we want to do is we want to ask a question to this system. So how many islands are comprised of Japan? We're going to encode this question using the same BERT model, right? We've got this BERT model above. We're going to encode this sentence, this question, into that same BERT model here, which is a 384 dimension array of floats. And now here's where a lot of the similarity magic happens. So if you recall before, we have this king-queen distance, right? And the distance between king and queen, or 0, 1, 1, 0, is how we calculate, okay, these are similar objects in vector space, right? And so we're going to do the same thing here. We're going to calculate the distance between this question, how many islands are comprised of Japan, and all of the vector representations that we have from the Japan paragraph in Wikipedia, split by sentence, right? So said differently, which sentences are the closest related to this question, which helps us understand what's the answer to this question. And this is really, at its core, how a lot of these chat bots work that we see on websites, is they're converting the answers into embeddings, the questions into embeddings, and then calculating the distance in vector space between the questions and answers, right? And so that's what we're doing here. So we're calculating the cosine similarity, and cosine is just one example. Just like I said before with the dimensional depth, cosine similarity, Euclidean distance, dot product, these are all different algorithms that you can use to calculate the distance between vectors in a multidimensional vector space. So we're calculating the distance, and then we're just doing a bunch of manipulation and then presenting the output where the top results have the highest relevance score. So Japan is a part of a ring of fire and spans an archipelago of 6,852 islands. And that is the exact answer to the question that we have above, which is how many islands are comprised of Japan, right? And so if we want to take this a step further, what we can do is we can feed these results into a ChatGPT or any other large language model and say, hey, summarize this answer given these top number of documents returned. So we're not only returning one document, we're returning a number of, we could say, the top 5 documents as context into our large language model. And this is called retrieval augmented generation. And we actually get into that in a different video and a different article on the nux.ai website. So that's one really common architecture to expand these foundational vector embedding similarity retrieval systems, right? Another advanced concept is to train these models, to fine tune them on data that is specific to your domain, right? If you've got legal text, healthcare text, or even images, video, audio, etc., you want to train these models to generate different embeddings. And then you kind of work within them, work within these production workflows like a retrieval augmented generation to actually build out more sophisticated architecture. So that is really the extent of what we'll walk through in this Vector Embedding 101 video. If you have any questions or you want to kind of dive into more of these concepts, we've got a walkthrough which explains the breakdown that what we have, that what we shared today, the video, the code snippets, diagrams, etc. on nux.ai/vocab/vectors. And we have a whole series of AI concepts, architectures, and even technologies. So stay tuned, subscribe to this video, and check out the article itself. And again, my name is Ethan, building out nux.ai. We help you build AI applications. Thank you so much.